we start our lecture, and what's about numbering? I think now 10. Am I right? 10? Yeah. So 10.1, the fundamental theorem of calculus. Maybe you remember some time ago I mentioned fundamental theorem of algebra, although without proof. And now we'll discuss the fundamental theorem of calculus. Also it is called, so let me formulate, that is the fundamental theorem of calculus, or Newton-Leibniz formula. If f is integrable on AB and capital and f has a primitive, capital F on AB, then integral f of x dx can be computed using the following form. And there is a notation. We'll denote the last difference by this way. So capital F varies from B to A. That is just a notation. There is a very important tool which connects indefinite integral, because to find the primitive you need to find indefinite integral. And you see that it turns out that indefinite integrals are related to definite integrals, to Riemann integrals as we define them. So, proof. It's surprising that the best way to prove the theorem is to consider the right-hand side, not the left-hand side. Instead of integral, it seems we should somehow to try to understand how we can connect computation of integral with values of primitive. But surprisingly, the best is to start from the right-hand side. So we consider the difference, capital F of B minus capital F of A, and consider arbitrary partition P of the interval AB. If we take arbitrary partition, then this difference can be computed, can be expressed firstly like that, right? Just difference of the values of capital F at points xn and x0. And then we apply telescoping sum. So f of xn minus f of xn minus 1 plus f of xn minus 1 minus f of xn minus 2 plus so on f of x1 minus f of x0. So you see, we insert capital F of xn minus 1 with opposite signs, then capital F of xn minus 2 and so on. So we have telescoping sum, right? Then we apply Lagrange mean value theorem. How we apply it? We apply it to each of terms in brackets. So you see, for one term we have interval xj minus 1 xj, right? So on this interval, capital F is differentiable because F is a primitive. And what means primitive? Primitive means capital F prime equals to little f. So capital F is differentiable. So capital F is differentiable on this interval, and we can apply Lagrange mean value theorem, which says that for every such term, so on each of those intervals, we can find a point. Let us denote it by xi j, here j from 1 up to n, such that, for example, look at this, the first one, f prime at psi n, so the value of derivative at a point of our interval times the difference between ends of the interval, right? That is precisely Lagrange mean value theorem. Remember, if I apply it to capital F, f of d minus f of c equals to f prime at xi times d minus c. That is Lagrange mean value theorem, right? And I apply it to each of terms of that sum. So next, f prime at xi n minus 1 times xn minus 1 minus xn minus 2 plus so on plus f prime at xi 1 times x1 minus x0. And what is it? I can write it using the summation sign. So we summarize terms for j from 1 up to n, from the right to the left, right? Capital F prime at xi j times xj minus xj minus 1. Now, remember, capital F is a primitive, right? What means primitive? Capital F prime equals to little f. So, sum little f of xi j, and this difference was denoted by delta xj. So, what is it? That is precisely integral sum. So, look, we consider arbitrary partition and we start with a number, right? That is a fixed number. And this fixed number equals to an integral sum, right? So, partition P is arbitrary, but xi is not arbitrary, of course, right? psi is chosen in a specific way using Lagrange mean value theorem, right? And we know that integral sums, when norm of our partition tends to 0, they tend to what? One of the definitions of the integral, right? Integral sums tend to the integral. So we obtain here the integral. Now look, what is it? That is a fixed number which does not depend on partition, right? So, and it tends to another fixed number. It follows that in fact the left hand side equals to the right hand side, because both, I mean, main thing is that the left hand side in our case does not depend on the partition. So remember, everywhere we had equality sign, right? And theorem is proved. And let me emphasize that we need to suppose that f is integrable. So if little f has a primitive capital F, it doesn't imply that little f is integrable. So derivative might be not integrable. Let me give one example. Let's consider capital F of x equals to, let's say, x squared sine 1 over let it be x squared also. I think, yeah, x squared. This would be okay, I guess. For x not equals to 0 and 0 x equals to 0. That is capital F of x. Okay, what is about derivative? F prime of x equals to, okay, we differentiate 2x times sine 1 over x squared plus x squared times cosine 1 over x squared times minus 2 over x cubed by the chain rule, and it gives 2x sine 1 over x squared minus 2 over x cosine 1 over x squared. Of course, this computation is valid only for x not equal to 0, right? But we can compute also capital F prime at 0 as well. How? Just by definition. That is limit as delta x tends to 0, capital F 0 plus delta x minus f at 0 over delta x. That is by definition of the derivative. Look, f at 0 is 0, and when delta x tends to 0, we should suppose delta x is not equal to 0, right? It tends to 0, but it is not equal to 0. So I replace values of capital F, and we obtain delta x squared sine 1 over delta x squared over delta x. That is delta x times sine 1 over delta x squared. And what happens with it? We have infinitely little expression, right? Infinitely small, right? And that is bounded. Sine is bounded. So multiplication of a bounded expression, bounded function onto infinitely small gives us infinitely small. It tends to 0. So it means we have f prime of x equals to little f of x equals to, let me collect everything what we computed up to now, x not equals to 0 and 0 if x equals to 0. So we have a function little f has a primitive capital F, right? But look at the function little f more carefully. What happens with values of f of x, little f of x, as x tends to 0? We know cosine alternates, right? Between -1 and 1, right? And 2 over x tends to infinity, right? So it means that the function little f of x is unbounded in a neighborhood of 0. So it means f of x is unbounded, for example, on -1, 1. And if f is unbounded, then f is not integrable on AB. We know that there is a necessary condition for a function to be integrable. It should be bounded. And little f is unbounded. So you see, little f has a primitive, but it is not integrable. So we need to suppose both things. Of course, we should suppose that f is integrable, otherwise what is written as integral, right? That is definitely is necessary. So both conditions are necessary in the sense that we cannot omit them, one of them, right? So in fact, you see that this example had unbounded little f. But there is essentially more complicated example of a function which is bounded, has a primitive, but is not integrable. That is essentially more complicated, and I will not give it. Okay. Now, no questions. Let us consider a very particular case, but most important, which is used most often. So corollary. Corollary. If f is continuous on AB, then f has a primitive capital F on AB and integral f of b minus f of a. In fact, that is a version of the fundamental theorem of calculus which is used most often for continuous functions. And proof of corollary, how it was, okay, I don't remember. Theorem about indefinite integral, not indefinite, about integral with variable upper limit says that for any x in AB, derivative of that integral with variable upper limit is equal to the function at x. So, theorem about integral with variable upper limit says two things. First, that this integral is continuous function of x always, and that for every point of continuity, if we put x naught here, then derivative at that point x naught equals to little f of x. That is what says the theorem about integral with variable upper limit. Of course, here there are particular cases, namely x equals to a and b, right? Where we should talk only about one-sided derivative, right? Because we don't consider our function to the left of a or to the right of b. So when I consider here derivative, for example, at a, I should consider only right-hand side derivative, right? And if we are talking about derivative at b, we should consider only left-hand side derivative. Okay. So, it follows that capital F of x, which is integral f of t dt, is a primitive of f on AB. So, our function f is integrable, and integrable, there was a theorem about it, that every continuous function is integrable on AB, and also it has a primitive. So both conditions of our theorem are satisfied, hence we have the desired equality. So corollary is proved, and there are some situations when we need to consider something a little bit different. So let me mention it. So definition. Suppose f of x is continuous on AB with possible exception of finitely many points. Many points. Then capital F is called a generalized primitive of f on AB if f prime of x equals to f of x for all x in AB except for discontinuity points of f. So remark theorem 1 is valid if a primitive is replaced by generalized primitive. I'll not prove it. You should just consider several intervals where our function is continuous and apply the theorem together with a theorem. We had a theorem about that if a function is continuous on an open half interval, right, and is bounded on that interval, then it is integrable over the closed interval AB. But I'll not do it in details, so but later I'll use it for some other purpose. Okay, that is about the fundamental theorem of calculus. So now this theorem gives us a possibility to compute Riemann integrals without definition, because it was a very bad idea to try to use the definition of integral to compute the integral, because how to compute limits of those integral sums, that is very complicated fact. So let me consider another section, 10.2. Let us call it methods of computation. Of Riemann integrals. The first, okay, maybe a few words. First of all, of course, the first method is the fundamental theorem of calculus, right? Because how to compute the integral. Find a primitive using indefinite integral and substitute, right? That is the easiest way to compute a Riemann integral. If you want to compute definite integral, to distinguish between indefinite integral and Riemann integral, we call it also definite integral, right? So if you need to compute definite integral, firstly find indefinite integral, or what is the same, find a primitive, and then substitute into the fundamental theorem of calculus. But sometimes it is more convenient to proceed with definite integral from the beginning, and then we formulate theorem 1, that is integration by parts. Indefinite integral. If f, g are continuously differentiable on AB, then integral from A to B f of x g prime of x dx equals to f of x g of x from A to B minus integral f prime of x g of x dx. Here I use that notation for substitution. Proof. Observe that f of x times g of x is a primitive of f prime of x g of x plus f of x g prime of x. Why? Because what is primitive? Primitive is a function such that its derivative equals to the function under question, right? So derivative of product is precisely this one, right? So it means there is indeed a derivative, right? So moreover, what means continuously differentiable? It means derivatives are continuous. So we have product of two continuous functions that is integrable. Sum of two integrable functions is integrable. So this expression is an integrable function on each interval, including interval AB. Oh, just on AB, of course, because we cannot consider our functions outside of AB in general. So, okay, maybe I should mention here it also on AB. So, by Newton-Leibniz formula, implies that integral from a to b f prime of x g of x plus f of x g prime of x dx equals to f of x g of x substitution from a to b. And then look at this, and you see that is precisely what we want to prove. Just move the first term from the left hand side to the right hand side. That's it. So next is substitution formula. So, theorem 2, substitution formula for definite integrals. If, okay, let us consider the simplest way. G of t is strictly monotone and continuously differentiable on alpha beta G of alpha beta equals to AB, and F is continuous on AB. Then integral from a to b f of x dx equals to integral from alpha to beta f of g of t g prime of t dt. Proof. Okay, let's prove it. after the break. So let's have a break. So the proof of substitution formula. Here, first of all, we observe that both sides are well defined. Why? Because here we have superposition, composition of two continuous functions that is also continuous, and g prime is continuous as well, so we have product of two continuous functions and everything is okay. Then what we should do, we should consider f of g of t f of g of t, where capital F is a primitive of little f on AB. We know that capital F exists by continuity of little f. Then take a derivative. Take derivative. So, by the chain rule, what we know? Derivative of composition equals to capital F prime at g of t times g prime of t. And capital F prime equals to little f of g of t times g prime of t. Hence, by Newton-Leibniz formula, integral from a to b f of g of t times g prime of t dt equals to what? You see, what is written here? Little f of g of t times g prime of t has a primitive capital F of g of t. So, according to Newton-Leibniz formula, we have this, here alpha beta. We have this equality. Then substitute capital F g of beta minus capital F g of alpha. Okay, let me. I made a mistake in the formulation. Strictly increasing here. I made a mistake. Otherwise, I should change a sign. So, then look, for strictly increasing function, g of alpha by our supposition is precisely a. So we have f of b minus f of a. And again, by Newton-Leibniz formula, that is precisely integral from a to b, little f of x dx. That's it. So the proof is completed, and let me discuss a little bit this, first of all, this increasing or decreasing. What to do for decreasing function g? Look. So in practice, if we want to compute g of x dx by substitution x equals to g of t, then what we should do? We have to replace x everywhere as it was for indefinite integrals. Like, so you see dx equals to g prime of t dt, right? But also, what is important, we should look at x equals to a and replace it by what we have. So, if x equals to a, then t equals to what? So, if g is strictly increasing, right, like it was here, then we have here alpha beta, g is increasing, right? And if g is decreasing, then what will happen? We should change the order, right? So it will be beta alpha for g is decreasing. And then what happens? We should replace everywhere. So x equals to a is replaced by beta, right? B is replaced by alpha, f of g of t times g prime of t dt. And it means we have minus integral from alpha to beta, f of g of t, g prime of t dt for decreasing, okay, for decreasing function, for decreasing g, right? So for decreasing functions, we should put minus if we want to preserve the order. I mean, alpha should be less than beta. Okay. Okay. That is for decreasing functions. Okay, then maybe more complicated remark. You see, I supposed here f is continuous. We know that composition of two integrable functions need not to be integrable, right? That is one reason why I supposed that f is continuous. Another reason is that even if we suppose this composition is integrable, if we suppose this composition is integrable, I mean, forget about continuity, right? So suppose f is integrable and composition is integrable. Even in that case, look, another way to prove the substitution formula could be to consider integral sums for the left-hand side. That is, sum j from 1 to n, f of psi j delta xj, right? And then, for example, what are delta xj? Xj are xj minus 1, and in principle we can consider here, apply here Lagrange mean value theorem for if we suppose g is strictly increasing. Then by Lagrange mean value theorem, this can be replaced by g prime at a point eta j, so delta tj. So xj minus 1 equals to g prime eta j times tj minus tj minus 1. G of tj equals to xj. That is Lagrange mean value theorem. Then you see there is not an integral sum, right, for f for this one, right? It is not equal to the sum in general. That is an integral sum for the integral in the right hand side, right? If we write down integral sum for this integral, then that is another story. So in principle it can be proved nevertheless under slightly less restrictive suppositions, but I will not do it. So the main reason why it is more complicated is here. It's here. Okay, so in your lecture notes it is mentioned also. Yeah, it is mentioned. Okay. Now let us consider next section. So today is a day of several sections. So section 10.3. Mean value theorems for integrals. So let's start with discussion of simplest cases. Let's start with one function and I will recall estimation of integral. So denote M is infimum f of x on AB capital M is supremum f of x on AB. Then M times B minus A less or equal integral from A to B f of x dx less or equal capital M times B of A for any f Riemann integrable on AB. Integrable. So instead of repeating words integrable, I'll write for any integrable this one. That is just a consequence of estimation of integrals. Why? Because you see f of x less or equal to m, hence integral, in fact monotonicity property, better to say, m dx, and we know primitive for a constant is m times x, that is m b minus a. And analogously we prove the left hand side, right? A corollary of estimate, if f is Riemann integrable, m less or equal f of x less or equal capital M for all x in AB, then there exists psi in the interval such that integral from a to b f of x dx equals to psi times b minus a. And proof is given, because you see integral is somewhere in between those numbers, hence it is equal to something between little m and capital M times b minus a. So proof was given before. Corollary 2, if f is continuous on AB, then there exists C in interval AB such that integral f of x dx equals to f of C times b minus a. In fact, we can assert there exists a C strictly between A and B, I mean in open interval, but I don't want to spend time to prove it. So these are just consequences. Why it is true? We need to apply corollary 1, so proof, apply corollary 1, and Bolzano-Cauchy intermediate value theory. value theorem. So we know if the function f is continuous, then infimum and supremum both are attained by Weierstrass theorem. Hence, for arbitrary psi between values of our functions, right, there exists a point in AB where f of c equals to psi. So just apply corollary 1 and Bolzano-Cauchy intermediate value theorem says there exists C such that psi equals to f of c. That's it. Okay, now the first mean value theorem for integrals. Theorem 1. The first mean value theorem for integrals. Suppose f, g are integrable on AB. G is non-negative. Negative. On AB, m less or equal f of x less or equal capital M for all x in AB. Then there exists psi in the interval little m capital M such that integral from a to b f of x g of x dx equals to psi times integral g of x dx. Proof. So the inequality implies m times g of x less or equal f of x g of x less or equal capital M g of x for all x in AB. Why? Because g of x is non-negative by supposition. So we multiply an inequality by a non-negative g of x. Then inequality is preserved, right? For 0 it will be equality, but it doesn't matter. Then estimate of integral gives us integral from a to b mg of x. Not estimate. Why? Sorry. Monotonicity of integral. Less or equal integral from a to b f of x g of x dx less or equal integral from a to b m g of x dx. So, using properties of integral, I can put m outside. Then look. Now, we should consider two cases. Case 1. Integral g of x dx equals to 0. And the function is non-negative, right? So it means that what follows from this equality? It follows that the integral f of x g of x dx equals to 0 as well, right? And then look at what we want to prove. Both right-hand side and left-hand side are equal to 0, right? Hence, it is valid for arbitrary xi. We want to prove there exists xi, but now the equality is valid for arbitrary xi. So, don't need to prove anything else. Case 2. And remember that the function g is non-negative, right? So it means this integral is non-negative as well. So the case when it is 0, we considered. What remains? Integral is positive, strictly positive. Then what we have? Less or equal integral f of x g of x dx over integral g of x dx less or equal capital M. So I divided both sides, not both sides, three sides of our inequality, right, by the same positive number, right? And what it means? There exists xi in between little m, capital M, such that this is precisely xi. And that is what we want to prove. So, corollary. Corollary 1 is precisely what we said before about estimation. So, f is Riemann integrable, m less or equal f of x less or equal capital M, then there exists xi in the interval little m capital M, such that integral from a to b f of x dx equals to xi times b minus a. So this we considered before, we proved it by estimating, but now you see this is a particular case. So proof, put g of x equals to 1. Identically. So take g of x equals to 1. We see here integral of f(x), and integral of g is precisely b minus a. That's it. Corollary 2. If f is continuous, on AB, g is non-negative, g is Riemann integrable, G is non-negative. Or maybe then there exists C in AB such that integral from A to B f of x g of x dx equals to f of c times integral g of x dx. So you see, we know that if f is identically constant, f is a constant, we can put outside, right? And now it's a little bit similar, right? Even for arbitrary function. But it should be continuous, and of course we have a value at a point. So there exists a point where the value of the function is so nice to obtain this result. Proof, how? Proof, combine theorem 1 and Bolzano-Cauchy intermediate value theorem. Value theory. So, just similar. Okay, now about the second mean value theorem. Second mean value theorem is more complicated in proof, so I'll not give the proof here. And I'll give it without proof. Theorem 2. Second mean value theorem for integrals. If f is integrable, G is monotone, then there exists psi in AB such that integral from A to B f of x g of x dx equals to g of A integral from A to psi f of x dx plus g of B integral from psi to B f of x dx. And that is also called Bonnet formula. Bonnet's formula. In fact, one can prove some particular cases if you suppose additionally, for example, if G is non-decreasing and non-negative, then just that one is valid. If it is non-decreasing and non-negative, then that one. But yeah, I think the proof is rather complicated. So it uses very nice formula, very nice transformation, which is called Abel transform. And maybe the proof uses Abel's transform. And maybe I'll explain what is it. Abel's transform. That is when you summarize such numbers. Look, you summarize products ui times differences vi minus 1. Then write down explicitly what is it. u1 times v1 minus v0 plus u2 times v2 minus v1 plus so not plus un times vn minus vn minus 1. Then let us group. So first of all, open brackets and then group all terms using v as common multipliers, not u. So what it gives? Look, vn has only 1 times un. Also v naught has only 1 term. All other terms are like, look, v1 times u1 minus u2 plus so on plus vn minus 1 times un minus 1 minus un. So we obtain very similar to v naught u1 times minus sum j from 1 up to n, v up to, n minus 1, vj times uj minus uj minus 1. So look, the terminal sum is very similar to what we had before, right? And if you compare it with integration by parts formula, then it is very similar. So that is why Abel's transform is also called summation by parts formula. So because it's very similar. Okay, but as I said, I will not give the proof. So that's all for today. Thank you for your attention.